Yeah, thank you so much. Thank you for the invitation. So this is joint work with Dervan here in Glasgow. So the way I want to break up this talk is to give like a bit of motivation of why you would want to study these kind of problems, really. And then I'm gonna give kind of like an introduction on divisorial stability, since it's a very, very recent notion. I just want to give at least like an introduction of how you define it, how you want to study it, why it's kind of different from case stability, and all these things. Why it's necessary also, and then I'm going to talk about these finite covers. So the main work with Uri. So to begin with, when we look at stability theories, like in modern math, the aim we have usually is kind of like a twofold aim. So we have two goals that we want to satisfy. The one is which is kind of like the end goal, if we manage to achieve this, is to construct some moduli spaces, which will help us with some classification problems or parameterization problems. The second one is fairly more recent. So the first one kind of ties with GIT, and which is like the granddaddy of all these stability theories. The second one is more recent. It's these links that you can obtain with differential geometry. So I say here answer questions in differential geometry. Essentially, you want to develop some notions of stability where the stable objects will have some properties in differential geometry, usually some metric structures. And the motivation behind especially the second one, is really case stability. So case stability is a fairly recent theory. It was developed in mid-late 90s to early 2000s by a bunch of people, mainly Tian and Donaldson. And the primary reason why it was developed was to answer which Fano varieties admit a Kähler-Einstein metric. So this is also known as the Yau-Tian-Donaldson conjecture. It's a very important conjecture in complex differential geometry, primarily because these Kähler-Einstein metrics play a really important role in the study of differential geometry. They had pretty much dominated the study for the past 20, 30 years. And Fano varieties, on their own hand, if you don't really know what they are, just a very, very small introduction to them. They're varieties that have an ample anti-canonical line bundle. So this line bundle here has to be ample. If you think things from more the differential complex geometric side of things, they have a positive Ricci curvature. So if you want to have an idea of how to think of them, you can think of them as higher dimensional analogs of the sphere. And they're really important also in the study of algebraic geometry, and beyond there, they have ties with the MMP. The MMP essentially postulates that they are one of the fundamental building blocks of the other varieties, and they also have ties with mirror symmetry, so they're a very important item of study in algebraic geometry in the past 10, 20 years, essentially, and even more. So case stability in itself, I mentioned GIT before. Case stability is really heavily modeled on GIT, and really what it tries to do is it tries to study like bring essentially GIT stability in terms of varieties. So in order to be defined, you need these things called test configurations, which play precisely the role of one parameter subgroups for varieties, in the sense that you want to study C-star degenerations of varieties. So test configurations are the object that allows you to do so. And here, we mentioned Fano varieties before, but the whole point is that if I take a polarized variety, so a projective variety with an ample line bundle, so a pair like this, essentially, the test configurations can be defined in generality. It doesn't have to be only for Fano varieties. When we usually consider Fano varieties, the line bundle L is just minus kx, so it's the ample anti-canonical line bundle. But this is a general construction, and it goes kind of as follows. So a test configuration for this project, this polarized pair, this polarized variety, is a variety, this currently X, which also has a Q line bundle L. So we usually think of these as when we write a test configuration, we write pairs like this. And then again, as I mentioned before, you want to study these C-star generations. So you want to have a C-star action on this variety, curly X, lifting on the line bundle. And you also want a flat G equivariant morphism, which goes like this, such that you can think of each fiber, which is not the zero fiber, so the central fiber, to be isomorphic to your pair, essentially. And then your central fiber is what gives you the structure of these C-star generations, the limited generations for varieties. So because K-stability mimics this GIT construction, in order to determine stability, you want a notion similar to the Hilbert-Montfort weight or the Hilbert-Montfort numerical criterion. And this notion in K-stability is given by the Futaki invariant or the generalized Futaki invariant, or sometimes the Donaldson Futaki invariant. So this is an analytic invariant. In the case of Fano varieties, one way to think of this is an analytic invariant which measures the obstruction to having a Kähler-Einstein metric. In more generality, it can be an obstruction to having different types of metrics, which I'll mention in a little bit. So the next part is a little bit technical, but not so difficult to understand. Essentially, like this definition of this Futaki invariant, it goes kind of like this, where you take dk here to be the dimension of the zeroth cohomology, a0 of x, and you have like the kth exterior power of your L, where k is a natural number. And this turns out that you can have this composition, you have this expression as a polynomial, where you have these terms a0, it's not a6, sorry, a0, k to the power of n, and then you have a1, k to the power of n plus 1, and then lower degree terms, where these ai are rational numbers. And then when you consider the central fiber, you also have a C-star action on the central fiber, which lives in the cohomology. And this action also has a weight, where if you study the equivariant Riemann-Roch theorem, you can decompose the weight also into this polynomial decomposition here. And then the generalized Futaki invariant for any test configuration is essentially given by this formula here, which is not particularly important. It's more of being, for continuity really, and for completeness in the talk, to define K-stability. So the pair XL is K semi-stable if for any test configuration this curly X, curly L, the Futaki invariant is bigger or equal than 0. It is K polystable if for any test configuration, the Futaki invariant is again greater or equal than 0, and the equality happens only if this test configuration is trivial. And it is K-stable if for any test configuration, again, the Futaki invariant is greater or equal than 0, and the equality happens if X, this curly X is what we call the product test configuration. So it's X times A1. So this is, as I mentioned before, this is a general definition. It doesn't really depend on Fano varieties. It can be defined for any projective variety with an ample line bundle. But where K-stability has found its biggest successes is essentially in the case of Fano varieties. The first one, which essentially answers this goal 2 that we had, this connection with differential geometry, is this Theophylline theorem due to Chen, Donaldson, Soon. Which says that if you have a Fano variety, it admits a Kähler-Einstein metric if and only if it is K polystable. And here I'm kind of cheating because essentially I'm considering this polarized pair. So I'm not considering any line bundle. I'm considering the specific anti-canonical line bundle in my notation so far. So this is what gives the link between K-stability of Fano varieties and differential geometry. But in recent years, this notion of K-stability has been expanded. So it has been expanded through differential geometric properties, and these differential geometric properties, this birational geometric properties, and birational geometry in general has allowed the construction of moduli spaces. So this has been done in kind of steps. The first definition essentially would be to have X to be a projective variety, and then to have a birational morphism from X, where Y is also a variety. and a prime divisor f inside of y will be called a prime divisor over x, which we usually denote by this notation, just for ease. So now when we have this setting, we can define some invariants on it. The first one, which is very natural, is this log discrepancy, which is this term here, and this term is 1 plus the order of f alongside the difference between the canonical class of y and the pullback of the canonical class of x. And we can also define another invariant, which is called the S invariant, which is given by this formula here. So this is the formula for the S invariant. This S invariant kind of acts like an expectation value, really. It also measures, like, as you can see, we keep removing bigger and bigger parts of f from our the pullback of our canonical class. So it kind of measures how much of f we can put in the canonical class. This allows us to define the beta invariant, which is given by this formula, ax. So the log discrepancy minus the S invariant. So here the volume, I kind of skipped it over. This is just how it's defined. Is the lim sub of all of these dimensions here over this this number at the bottom. The properties are that if f is a big line bundle, the volume is bigger than 0. Sorry. Yes, and then if f is an f, then the volume can be just given as the nth exterior power, where n is the dimension. The reason why this is important, all this kind of like definition, is that if this theorem due to Fujita and Lee, where it's essentially introduces valuative criteria for K-stability, where if x is Fano, then the pair x minus kx is K-semistable, if and only if this beta invariant of x is greater or equal than 0 for all prime divisors e over x, and then it will be K-stable if this is bigger than 0. So the reason why you want these definitions is that although the definition through test configurations is really important and it gives you all these links to differential geometry and complex geometry and can answer the Theodoros conjecture, in reality, you can't really use these definitions in order to say that something is K-stable. It's very, very hard to be able to just use these definitions to detect K-stability or even find properties of K-stability. And these properties of K-stability are necessary if you want to study the potential of having moduli spaces. So because of the introduction of these techniques, and obviously I'm skipping a lot of theory and history here, but in the past 10 years, essentially, these techniques have allowed this particular theorem, which I list a lot of people here. There's probably more involved in this theorem. It's a collaboration between many people. But the key point here is that there exists a moduli stack. So this moduli stack here, this curly MK, which admits a projective moduli space, this MK. So the moduli stack is parameterizing these K-semi-stable Fano varieties, and the projective K-moduli space parameterizes K-polystable Fano varieties. And again, here the polarization is always minus Kx. So this is really important. It's a really big achievement of K-stability for Fanos. It really answers the first call, which we mentioned that stability theory should, in theory at least, or hopefully should give some moduli construction. And K-stability really achieved this for Fano varieties. So it seems this is the right definition for moduli spaces for Fano varieties, and it's a really big achievement in the past, 10, 15 years, really. Then a natural question to ask is, since we have achieved all these things for K-stability of Fano varieties, and obviously K-stability of Fano varieties is just one potential, like it's a subclass of all the problems that we can answer. If we consider a general polarized variety, so an arbitrary polarized variety like this, where we don't necessarily have to X be Fano and L to be the anticanonical line bundle, can K-stability shows something similar to the first goal. Essentially, can K-stability construct a moduli space similar to the case of Fano varieties? So that would be kind of like a holy grail achievement of K-stability from classification problems perspective. For the second goal, which is this goal linking differential geometry and stability theories, K-stability already has this link, at least conjecturally. So the generalized Yato and Donaldson conjecture predicts that here we have K polystable if and only if we have the existence of CSK metrics on X. And CSK metrics are a particular class of metrics which are really important in complex differential geometry. They've really dominated the study of the field for 70 years. It's essentially the study of finding canonical metrics on a Kähler manifold, and they're really important for differential geometers. So even this link, if answered, would be a really important step forward. So the Yato and Donaldson conjecture is still open. It's only proven in one direction. So I think you can show that the existence of CSK metrics gives you something that should be a uniform K-stability, which is a similar notion, which I'm not going to really define, but it's open in the other direction. So I've only talked about K-stability here. I haven't really mentioned the words divisorial stability so far. So you might ask, why do we need divisorial stability? Why is this notion important? And the reason is that when we consider a general polarized variety, this beta invariant we define above, this Fujita-Lee invariant that we define above, where I kind of cheekily defined it. If you remember, if you noticed, I defined it for any line bundle here. I didn't really restrict on the anti-canonical. And the reason I did this was to stress that, essentially to stress that this beta invariant, even though it can be defined for this polarization, it doesn't actually determine K-stability in the general sense. And the reason it doesn't work is it just doesn't capture K-stability. You don't have a theorem like Fujita-Lee, and you can't have a theorem like Fujita-Lee, precisely because Fujita-Lee essentially tells you that this beta invariant and the Donaldson-Futaki invariant agree in the case of Fano varieties, but they won't agree in the case of a general polarized variety. The other thing is that I mentioned this before, but working with test configurations is really, really hard to do anything. We can't prove any properties. So in reality, we want to introduce new notions. So we want to introduce new invariants, maybe, that will allow us to introduce valuative criteria. But up till last year, we didn't really know how to do this. And this was only recently done. So this new approach, which is used here, which I'm going to go over in a little bit, uses techniques from non-Archimedean geometry and differential geometry to study K-stability, and essentially it reaches the conclusion that you need to define this notion of divisorial stability. And this is the work of Boucksom-Jonsson from last year, from 2022, which is a very recent advance, essentially. So without further ado, I'm just going to give some preliminaries. So if I have, I'm not going to really explain what a non-Archimedean field is. The only thing you need to know is that I'm working over the complex numbers, and I'm taking what is called the trivial norm, which essentially is giving me a non-Archimedean field. The important thing here is that if X is a projective variety, I can define this Berkovich identification of X. So this is just denoted by X and by and being identifications. And this is the space of all semi-valuations of X. So we can think of valuations that start from the function field of Y, where Y is a subvariety of X. So in particular, we also can think of X as a subvariety of X, and valuations of X lie inside this Berkovich identification. And a particular subclass of these valuations is the space of divisorial valuations, this X div, where we just consider divisorial valuations. So divisorial valuations look like this. I take a prime divisor over X, and I find the valuation of the order of F, and this C is just a constant here. So this is the first definition, and the second definition is that I can take the space of continuous functions. So these continuous functions, phi from xn to the real numbers, which I denote by this C0x, which is in fact a Banach space, but it's not really important. And this has a dual space denoted like this. So C0x dual, which is the space of random probability measures. So these are this is a dual space to a function space, so these are probability measures, and we will discuss a little bit more how they come into play in the study of divisorial stability later on. So you may ask, how can we use these very abstract definitions in order to have any concrete result with K-stability? And the answer to this is, the first thing to do is to look at test configurations and try to see if we can alter our definition of K-stability and move from test configurations to maybe these functions or these measures. So we can define a function on xn, so a function lying inside this C0, and we can define it associated to a test configurations with the following idea. So we take a test configuration and we assume it dominates the trivial test configuration. And this is notation just to tell you that there exists a map, this map gamma, that takes you from the curly x to the product test configuration, to the trivial test configuration. Now, you may think that this may not always happen, but in reality, you can just take this rational map and then take a resolution of indeterminacy, and you can define this. You can define this for really any test configuration. So this is pretty consistent, but it's not super important. The whole idea here is that I take the class of L and I remove the class, curly L, and I remove the class of L, where I'm just abusing notation here. This is the pullback of the original line bundle I'm considering along gamma. I'm just abusing the notation here for ease. This is going to be a divisor. Then I can consider the central fiber. So x0 will be lying inside x, right? So this is, you can think of x0 as a divisor, which doesn't necessarily have to be reducible. So you can have this irreducible representation of x0 by cycles. So this EJ are reduced irreducible divisors essentially inside the variety curly x. And now we can define this function phi, depending on curly x, curly L, so the test configuration, via the following relationship. So you can look at what happens when we evaluate this function alongside this divisorial valuation, where if you notice carefully, this is a divisorial valuation on x, right? Because we have this map here where this is the projection. So we can consider divisors lying inside this curly x. So these divisors EJ as divisors, prime divisors over my x. So this is a good definition essentially. So this is supported on the divisorial side, so x div. And then this is essentially the evaluation. It's just some numbers. It's not really important. The important thing is that you can, in fact, associate a test configuration with a function on the Berkovich identification. And this gives kind of a motivation of maybe you should keep doing similar things in order to pass from test configurations to objects that you may have the ability to transform and change and study more easily. So the first definition on this side is what we call a Fubini-Studi metric. So this is a metric or continuous function, this phi of chi L, associated to this Neff test configuration. And here Neff test configuration, I'm just assuming that the line bundle curly L is an F divisor on curly x. And then I can also define PASH metrics, where PASH metrics are uniform limits of a sequence of Fubini-Studi metrics on this Berkovich identification. So these are functions, so you can think of them. You can think of some term like a uniform convergence of functions, and PASH metrics are uniform limits of sequences of Fubini-Study metrics. So an important definition that you can do here is what is called the Monge-Ampere energy of a Fubini-Study metric. So this is in fact what is called the energy of the task configuration itself, and it's given by the top exterior power of your Cayley L divided by n+1 times the top exterior power of L to the n, where, because I'm assuming these things to be Neff, I can be pretty confident that these top exterior powers exist. And then I can also extend this definition to PASH metrics, where I'm just setting this value here. It's a bit technical, but the whole point is that I'm taking infimum of all the energies of Fubini-Study metrics, such that essentially I have this property where essentially I say phi is bigger equal than psi, but all this means is that if these two things are induced by two different task configurations, I can find a third task configuration essentially dominating both of them, such that the difference of the classes, so this difference here, so this is again the pullbacks on this y that dominates both task configurations, is effective. And then we define this space of all the PASH metrics that have a finite energy. So this is the epsilon 1 is the space of finite energy PASH metrics. So the reason we want to do this...
Sorry to interrupt, Theo. What do you mean that dominates the other two?
So it dominates, oh yeah, sorry. It's this property that essentially like I can have y going to x prime and then y going to x. Dominates really, all it means is that if I have xl and yl and I say that y dominates x, I just have a map going like this. It's just notation, really. It's just like I can find a map between the two varieties, really.
Yeah.
And dominates means that y maps. Good.
Yes. Thank you.
So the reason why we want to do this is kind of like hidden. So this is more differential geometric than algebraic geometric, and it comes from how you actually define the Futaki invariant. I kind of cheated because I didn't want to go into this. Obviously, it would take too much time. But the whole point is that this Futaki invariant has what is called an entropy term and an energy term. And the entropy term is a bit more complicated, but the energy term is precisely what you see here. So instead of looking at the energy of the task configuration, where you may have issues of how you can compute it, you can look at this energy of the Fubini-Study metrics or PASH metrics, and you may be able to work with them easier. Essentially, that's the rationale of why you want to look at these things, at least. And the other thing is that you now have measures, so measures come into play, and I can consider a measure mu. I can define its norm. So its norm, in a way, plays the part of energy for measures, right? So measures are living in a dual space. So the norm, which is this thing here, it's not really a norm in the sense of like your linear algebra, because this is not a vector space or anything. It's just like notation. Here, just L denotes that I'm keeping track of what polarization I'm always picking. But what I'm doing is I'm taking the supremum over all finite energy PASH metrics on Xn, and then I really want a finiteness because I have this term here, which is the energy of phi, and then this is just the valuation, right? This is the valuation of phi along this mu, right? It's the usual dual space valuation that we're expecting from the two things. So again, we also have another term, which is this M1, which is all the metrics of finite, all the measures, of finite energy, or finite norm, if you want. And for those of you who are more familiar with the whole K-stability of Fanos and differential geometry, the next example is going to be, it's going to give you a motivation on why you want to study these things. So the first thing I want to define is this directional derivative. So one of the important results of Boucksom-Jonsson is that in fact you can define this this directional derivative, because it's not very trivial that you can actually differentiate along this function, that this function is in fact differentiable. But the whole point here is I can take an R divisor h on my projective variety x, and then I can take the directional derivative. So this guy here I've underlined, which is just the derivative of d dt, where t is evaluated at 0, where I take the norm, but now I'm not just evaluating in terms of L, I'm evaluating in terms of L plus th. So it's a bit more complicated because I also have to consider test configurations with respect to L plus th and so forth. So this is a quantity that's usually not very easy to compute, but it's nonetheless a really important quantity, as you will see in this next example. Here, I'm just denoting by delta C or F to be the Dirac mass supported at the valuation U equals C or F. So essentially, I have a valuation U, and then I want to essentially I want to say that this measure essentially is probability measure has probability 1 if a function is supported on this divisorial evaluation, and it has valuation 0, like a probability 0 elsewhere. This is essentially the Dirac distribution of this divisorial valuation, essentially. So like more formally, I want this to be 1 if essentially like f of u doesn't vanish. So that is what I want to say. So the example for those of you who are working mostly with case stability of Fanos is that if I take H and L to be the anti-canonical line bundle, if I take X Fano and I take mu to be a single, like a Dirac mass, then this directional derivative is in fact the minus S, the S invariant of F. So this is like really important. Obviously, this is highly non-trivial. You can't really see it from whatever I said up till now. So you kind of have to take my word for it. But trust me, this is correct. And it kind of gives you an idea of how these notions are starting to beginning to generalize the notions from this, divisorial stability or divisorial case stability, which was developed in 2016, 2017 by Fujita Lee, essentially. In a little bit, I'll give you more of a heuristic reason why you want these divisorial measures, as I name them here. So the reason here, so the definition before I go into the reason why you wanna have all these things is you have these divisorial measures. These are probability measures of the following form. So you just take a sum of you take some coefficients AJ, and you keep adding these Dirac masses of divisorial evaluations UJ. This is a probability measure, so this has to be equal to 1 because of exactly the probability measure, and this is a finite collection of divisorial evaluations. So then you define this M div to be the set of divisorial measures, and now with this definition you can start defining divisorial stability. So the first part is defining this entropy part, which is very similar to what we have seen before about log discrepancy. So the way you should think about these divisorial measures are they're convex combinations of divisorial evaluations in a way. That's what they represent, right? They represent convex combinations of divisorial evaluations. So this entropy term really, the way it works is by taking the log discrepancy term or the log discrepancy and just making a formal combination of the log discrepancy. So this is just a function from the divisorial measures to the real numbers, which is evaluated like this, where if you know this value here, this value is what is called the log discrepancy function, which you can define in valuations, which can be defined for every valuation, in fact, not just divisorial valuations. But the important thing here is that if mu is as above, so if mu has this form here, then the entropy of this divisorial measure is exactly the sum of the log discrepancies of the valuations, which if I assume that Vj is just Cj times ORD F, this is just this sum here. which let's see, fj. So this is exactly the sum of all the log discrepancies comprising this of this convex sum of divisorial valuations. So when we define this term, which we can essentially precisely because this log discrepancy function is well defined, this beta invariant for mu, and again I have x and a specific line bundle L, is the entropy term plus the directional derivative alongside kx. And if you notice from the previous example, again, if x is far known and L is kx as we want essentially, then this and mu is just a single divisorial measure. So just say that this is a delta or f, so not a convex combination, but just a single one. Then this beta invariant is this beta of sorry, this should be minus kx. Yeah, so if this is this beta of mu is precisely the beta of f, which is defined in the Fujita-Lee case. So we already know that essentially this new beta invariant kind of generalizes the Fujita-Lee criterion, the Fujita-Lee invariant. The heuristic reason why you want to consider why this whole thing makes sense is this thing called the non-Archimedean Calabi-Yau theorem, which essentially tells you that for every measure you can find a metric such that there's an operator, the Monge-Ampere operator, such that this thing is given like this. And then this Monge-Ampere operator has a very particular structure when you're computing it alongside task configurations. It's essentially a sum times some coefficients, which I don't really remember, times the delta distributions of the order of the EJs, where the EJs are, as before, the cycles of the central the central fiber of the test configuration. Whereas when you consider infinite varieties, you know that you only need to consider test configurations, special test configurations, where this is irreducible. So there exists only one. There exists essentially only one divisor, really. So just x0 is just e, as you can say, and then this is not a sum anymore, but it's not a formal sum. It's just one Dirac mass with some coefficient in front. So it makes sense why you want to consider the beta invariant to be just essentially why all these notions should generalize the beta invariant. Whereas in the general case where you do have this decomposition, you should expect combinations, essentially these convex combinations of these divisorial of the evaluations, or which are precisely these divisorial measures. So the notion of divisorial stability then can be defined, since we've defined this beta invariant, where something is divisorially semi-stable if for all divisorial measures mu on this xn, this beta invariant is bigger than 0, and it's divisorially stable. We call it divisorially stable, but this is essentially a uniform stability condition, because it's divisorially stable if we can pick an epsilon such that for all divisorial measures, this beta is essentially bigger than epsilon times the norm of mu alongside this L that we have defined. Now, another really important, behind all the heuristic idea of why this is important and why this makes sense, another important consequence of the work of Boucksom-Jonsson is the following theorem. Let me write their names properly. So if the theorem essentially tells you that if XL is divisorially stable, then it will emit a uniquely CSK metric, which implies that it's uniformly K-stable. So essentially, divisorial stability is a stronger even notion than K-stability. But the conjecture essentially tells you that these notions should be the same. And this conjecture is essentially the conjecture that divisorial stability is implying uniform K-stability is the Yau-Tian-Donaldson conjecture, essentially. So this Yau-Tian-Donaldson conjecture, the generalized Yau-Tian-Donaldson conjecture I mentioned before, is precisely this newly defined notion here, where essentially is reformulated, reconstructed through these non-Archimedean languages, where and taken a bit more in an algebraic geometric direction rather than a differential geometric direction, so an analytic construction. So I'm going to move now to the finite covers, which is the work with Rui. So as you may have noticed, it still remains pretty hard to compute these invariants. I mean, you have them, and you can reformulate the Yautian-Godolson conjecture, and you can say things about the divisorial stability a bit more than you can say about k-stability, but it still remains pretty hard to explicitly find that something is divisorially stable. And this finite cover situation is essentially a comparison result, which will allow us, when we have a more powerful machinery, to be able to find more divisorially stable varieties. Essentially, a comparison result, which essentially will tell us when the finite cover is divisorially stable, we expect that the variety itself is going to be divisorially stable. So I'm going to go over this in detail, but first I need to introduce kind of a notion of an equivariant divisorial stability, because it's essentially we need this notion of equivariant divisorial stability where we have a group action. So if I have a group acting on a variety X, then also the group acts on the set of divisorial valuations of this X div. And the reason is because it also acts on the function field. So this action on G of U is given when computed at F, is just given by U, a G pullback of F. So I can essentially define what is called a G invariant divisorial measure. So I have a divisorial measure as before. And a G invariant divisorial measure will be of this following form. Essentially, if I have all G, then mu can be rewritten in terms of this action on G of Uj. So these two things should be equal, essentially. Hence, G invariant. And I'm going to denote the space of G invariant divisorial measures by this again. So mu div G to denote the G invariance. Y here will be, or X in this case, will be to denote what variety I have, which will be more important later on. And then I can define G equivariance as divisorial stability and semi-stability, which in the following form, again, I want the beta invariant to be bigger or equal than 0 for all G invariant divisorial measures if I wanted to be divisorial semi-stable. And if I wanted to be divisorially stable, I require that for all divisorial, so G invariant divisorial measures, this beta invariant is just bigger or equal than, again, there exists an epsilon such that the norm of this mu, this beta is bigger or equal than epsilon times the norm of this mu. It's essentially the same definition, but broken down into G equivariant terms. So this setup for this result is the following. So I'm considering two varieties, two normal projective varieties with two different polarizations. So I have X Lx and Y Ly. And then the one thing I require is that I have a map pi between the two of them, where it goes from YLY to XLX, which is a Galois cover. And what I mean by that is essentially I have an action of G on Y of a Galois group with X being the quotient of this action. And I have two effective divisors, which I amply name delta X and delta Y for divisor on X and divisor on Y respectively. These are effective Q divisors such that ky plus delta y is the pullback along this map of kx plus delta x. So the main theorem we prove for this particular setting is the following essentially, which I should say that this is our theorem. So the whole point of this theorem is again this comparison method that gives you this, allows you to say that I can compare the divisorial stability of the cover to the divisorial stability of the variety. And in this case, what I didn't really mention, I should have, is that all of the constructions above about divisorial stability, k-stability, they can be generalized to log pairs. The reason I didn't do it is because it's much easier to discuss things for for just a variety, and then kind of extrapolate on how you would define it for log pairs. It's more for ease of notation and being clear. But the whole point is that you can also define divisorial stability and k-stability and all these notions for log pairs, and have what is called log divisorial stability, if you will. But the whole point here is that if I consider this log pair, y delta y ly, this is G equivariantly divisorially semi-stable or stable if and only if the corresponding log pair x delta x Lx is divisorially semi-stable. So it's precisely this comparison result, and it's really strong because it's also an if and only if statement. So there's no essentially what we will guys see from the idea of the proof as well is that how the idea of the proof works is by showing that the beta invariants for things actually agree, so that you get this if and only if. And the idea for proof of this, I'm not going to go over the proof itself, but the idea of proof and where the whole meat of the proof of this main result is to define pullbacks and push forwards for divisorial measures and metrics. So if I have a divisorial measure, let's say nu on x, I want to define a pullback that takes it to divisorial measure on y, and vice versa. So if I have a divisorial measure mu on y, I want to define a push forward on this divisorial measures on x. And I want to show these two things really. I want to show that the G invariant, the set of G invariant divisorial measures is isomorphic to the set of divisorial measures on x, and that the set of G invariant metrics on y is essentially isomorphic to the set of metrics on x. And the whole idea here that you do it essentially is by showing that these pullbacks are inverses really of each other for mu and nu respectively. Then you can show that that these things exist, and then just by careful comparison of all the terms that I defined above, so all these like terms of the beta invariance, so the log discrepancy, and the norms of everything, which is essentially the main heart of the paper, like how do you actually compute all these norms and director and derivatives? You can in fact show that the two beta invariants should agree. Essentially, whenever you take a G invariant divisorial measure on y, you can define a divisorial measure on x, and their beta invariants have to agree. And because it's an arbitrary construction, essentially the beta invariants agree all the time. So you essentially have the proof of the theorem. So using this, we managed to prove this other main result, which is like an interesting application really, which essentially allows you to use like an interpolation technique to find varieties that are divisorially, G-equivariantly divisorially stable, and that they will admit CSEK metrics. So the setup for this is that I can start from a divisorially semi-stable, So I can start from a divisorially semi-stable smooth polarized variety, this guy here, where Lx is again the amplitude line bundle on X. The only difference here is that it requires smooth. Up till now, I only required normal. There was no restriction on being something smooth. But here I require this to be smooth. And the point is that you can find a positive k such that if you assume these three conditions, so if you find a divisor inside the linear system of KL to be such that this is log canonical, so this guy being log canonical, this log pair xb being log canonical, and you define the finite cover of y, I guess we defined them before, with respect to x, branched along the divisor b, and assume that y is smooth, then y admits a CSK metric in the first term class of the line bundle Ly, where again, as before, Ly is the pullback of Lx alongside this Galois morphism. And the idea of the proof here is pretty similar. It uses essentially like an interpolation technique, which has found a lot of use in k-stability for finite varieties as well. The first thing you want to do is, and this is where this k plays a part essentially, is that if you can find such a b and k, so if you can find such a k such that every b in the linear system is log canonical, then in fact this pair is log divisorially stable. And then you use the interpolation technique, where if you assume that the pair XLX is divisorially semi-stable and that this is log divisorially stable, then the log pair XCB is also divisorially stable for all values between 0 and 1, including 1, obviously. So this is essentially the interpolation step. And combining 1, 2, and the main theorem, where now you consider, so you start from a divisorially semi-stable variety. You show that there exists a B such that the pair is log divisorially stable. So essentially the pair, this pair here is also divisorially stable. And then apply the main theorem. I wrote it in the wrong way, but it doesn't matter. So if you apply the main theorem, then this YLY is divisorially stable. And then we use this Boucksom-Jonsson argument, where how they showed essentially that something being divisorially stable implies the existence of CSEK metrics, where we use this Boucksom-Jonsson argument to show that G-equivariant divisorial stability will also imply the CSEK metric if we have something being smooth, and we prove the main theorem essentially. So a couple of remarks here. The first one being that, at least for the first theorem, I think, and that's where you can see, so for this theorem here, is that if you were trying to prove this result just by using test configurations to the definition of K-stability, I really, really doubt that you could achieve much, because it would be very, very hard to compare the Futaki invariants of the test configurations. At least you may be able to prove one direction, but you definitely shouldn't be able to prove both directions. So this essentially gives you an overview of why this divisorial stability notion is kind of handy, because you have these invariants. Okay, they may be they may remain hard to compute now, but because you have them, you can relate them more easily than you can manipulate them more easily and relate them more easily than you can with test configurations. So you can obtain results like this particular theorem. The second remark is that this theorem here, essentially, this theorem, the existence of the metrics really in the part of the theorem, so the last part of the theorem, is also a consequence of recent work of Arezzo, De La Vedova, and Shi. But the whole point about this other approach is this: it doesn't use divisorial stability, obviously, because it didn't exist when they put out the paper. It uses completely analytical techniques, which are very, very different from anything I really discussed here. And this kind of proof is really the first proof which is completely algebraic in showing the existence of CSEK metrics, really. So yeah, having said that, I'm just gonna stop here, and yeah, if you have any questions, I'll just take them. Yeah.